le Breguet, le bâtiment Breguet,
Ah,
qui leur
d'accord.
met de neuf.
Donc,
Mais ça devrait durer 3 à 4 ans facilement. Ouais.
eh ben, donc ça va être une période provisoire alors. Et moi, j'avais
Ouais.
l'intention donc de venir vous voir, mais bon, c'est pas fait. Mais peut-être au courant
Ouais.
au courant de cette semaine, je passerai juste dire bonjour.
Ouais, bah, je sais pas si tu vas croiser grand monde, hein, parce
Oui,
que
oui, la
moi, je
plupart.
sais que j'y serai pas beaucoup.
D'accord.
Je sais que j'y serai pas beaucoup cette semaine et puis après, ça dépend des uns et des autres, quoi.
Bon, bah, on continuera en Zoom alors.
Mais n'hésite pas, ou en Zoom, ouais, mais sinon, tu peux voir avec Nicolas aussi. Tu nous écris un peu à l'avance et puis on essaie de voir si on peut être là.
D'accord, parfait. Okay, let's start. Hello, everybody. I hope that everything is okay
Hi.
and everything is hearing. Okay, we are very pleased to have François Orieux, one of my old colleague in Laboratoire de Signal System, and Lee Wang is going to present him and start the seminar. Lee.
Yes. Can you hear?
Yes.
Yeah.
Okay, welcome, François. Let me do a little presentation. François Orieux is an associate professor at the University Paris-Saclay and a researcher in the Laboratoire des Signaux et Systèmes, Signal and System Laboratory, and in the inverse problem group. And he's also an associate researcher with the Institute of Spatial Astrophysics. His research mainly focuses on Bayesian methodological approaches for ear-post inverse problems, with examples of applications in astrophysics and biological microscopy. So you can start your presentation now.
Yeah, okay, thank you very much. I will share my screen. Okay. Okay, do you see my screen?
Yes.
Yeah, okay, thank you.
The background is in black, is that normal?
No, I don't think so. Okay, so I will try another way. And this way, do you see it?
No, it's the same.
It's still black. Okay.
No, but
so I don't know why is it
but
like this.
when you put it on full screen, it's all black. And now it's not. The background is black, and yes.
Okay. Okay, so I will try something else. So I will disconnect. If it's okay for you, I will disconnect and I come back. Okay?
Okay.
I'm sorry for this.
No problem.
Is it okay for you? Okay, sorry.
Yeah, no problem.
During the time that François is going to come back, just a few words that we have started this series of seminars since December of last year. And we hope to have at least 1 or 2 seminars every month. One of the main objectives of this seminar is to try to propose cooperation with the seminarists in the future. So we have to follow the discussions, and in a few months we will try to have a common seminar with all the past seminarists, and we will try to see what will be the subjects in which we can do some international cooperation.
Okay, here we connected.
I'm back.
Okay.
Yes.
Okay, so now, do you hear me?
Yes.
Yes.
Okay. So I will now try to share my screen. I hope it will work.
Yes, this is good.
It's okay now?
Still the background of the slides are black, but it doesn't matter if we can see.
You must see my slide.
Yes, yes.
So you see my slide now?
Yes.
Yes.
So
Okay.
the background is black, but we can read.
Okay, if I show you this, you see the image, for instance?
Yes.
Okay. Okay. Okay, so thank you for the invitation. So my name is François Orieux. As Lee said, I work in the laboratory of signal systems. And I will speak about large non-stationary field simulation with application to image reconstruction. So some word about my co-workers, because I didn't do this alone. So first, there is Olivier Ferraud, who work at EDF, which is a big French enterprise, and is a manager now. Jean-François Giovanelli, which is a professor at Université de Bordeaux, and I think he'll talk in your seminar too.
Yes.
Yeah, and Raphaël Chinchilla, who made an internship with me and has a strong contribution in the work I will show you now. So some word about the laboratory. So there is 3 institutions, that manage this laboratory. There is l'Université Paris-Saclay, Centre National de la Recherche Scientifique, CNRS, and Central Supélec, which is an engineering school. And there is 3 poles, and personally I work in the signal and the statistic pole, who mostly work in image, speech, vision, or statistical learning. And in this pole, there is 2 groups, and I work in the inverse problem group, who make a lot of research in inverse problem fields. For instance, estimation when you have missing data or degradation of your data, or when you must use regularization. And we use a lot of, so we develop methodological work in the field of Bayesian and variational approach, machine learning, sparsity, wavelet. And personally, here today, I will speak about stochastic sampling. And we applied these methods in many applications: tomography, non-destructive testing, signal image estimation. Personally, I make a lot of contribution in astronomy and microscopy. So let's start with the beginning. If we want to do inverse problem, we must have a forward model. I use this slide also for the notation. So I will consider that there is a known interest of interest, which are x, and some unknown of non-interest, theta. And all these parameters go through forward models that produce data that are corrupted by noise. So it's quite general. Here, we will have forward models that are linear, but can be quite large. And especially, they will not be stationary. It will not be a deconvolution. So this framework, there is a lot of application case. So there is deconvolution, super resolution, tomography, and most of the time the problem is ill-conditioned. So, for instance, there is a lack of information because you have some missing data. The forward model does not observe all the unknown. Here we will consider that the unknown is quite large. Well, now with big data and machine learning, I'm not sure about what is large, but I still continue to say it's large because if you want to estimate an image which have 1 billion parameters, if all these parameters are correlated, the problem will be quite difficult. So a small classical or academic application, the super resolution problem. So I consider that you have a true image, high resolution true image, and that you have a set of low resolution image. And what you want is from this set of low resolution image, you want to estimate the true high resolution image, with the fact that there is small shift between this low resolution image. So here you have your high resolution image, you have a convolution followed by a subsampling. So you have a nil-poset problem because the convolution introduces instability in your solution, and you have probably missing data because of the subsampling. So the common approach for this problem, there is two main common approach. The old one, which is the MAP, maximum a posteriori approach, where you define your solution as the minimizer of a mixed criterion. First one about data adequacy, so you want to estimate a true image that reproduce well your data. But since your problem is ill-posed, there is not one unique solution, or your solution is stable. So you introduce additional criterion to have a well-posed problem. So if you choose a stationary prior with L2 penalty for the regularization, you have the classical regularized linear square that write like this, and for which we have an explicit solution, even if you not necessarily is able to compute it. You can also use a smooth penalty, but that are convex and non-quadratic, for instance, Huber one. or you can use a non-differentiable penalty like the L1 norm, which produce a lot of methods. For instance, the lasso algorithm. You may also want to use non-convex regularization, like the L0 support regularization, which conduct to another lot of methods like branch and bound, orthogonal matching pursuit, or other ones. And of course, now you have a lot of methods based on machine learning, so regularization by denoising, plug-and-play approach, unrolling, the GAN approach, or simply a simple feed-forward network that have a lot of good success for natural images and single image super resolution. I think that now for the common people that just want to restore their the photo from their mobile, I think that the feed-forward network we have now are quite good. Now I feel that there is some questions that are rising. So I will write here the map, classical map approach. The first one is when the regularization parameters are unknown and you want to estimate it jointly with the data. The other problem that I did not mention here, or that is related, is when you want to apply your method to non-seen data in a machine learning approach. If you want to do a hot distribution reconstruction, so you want to make to apply your network to an image that does not look the data you have in your database, it's a non-supervised problem. So how you estimate or how you tune your hyperparameter for unseen data. The other problem is estimation of parameter of the operator, like the forward operator or the regularization operator. You may want to have some degree of freedom and you want to estimate this parameter. And the last one is about the uncertainty. That is also affected for the machine learning approach. You can estimate an image, you can produce a result, but what is your confidence to this estimation? So the Bayesian approach is a classical answer to this problem. In that case, you build a posterior law about all your unknown parameters, so the unknown of interest, like the image, and the parameter of non-interest, like the hyperparameter or the regularization parameter. And if you apply your Bayes rule, you have the likelihood and the prior law. So you must model your probability law, and you use your prior on the unknown of interest to have at least a well-posed problem that compensate the problem from the likelihood, and you have a prior law for the extra parameters. For instance, the hyperparameters or the label if you work in segmentation. So I will show you some contribution in the case of conditional Gaussian model. And I say it's a comprehensive conditional model because if you are able to simulate Gaussian complex Gaussian law, you are able to do a lot of things. You are able to easily estimate the hyperparameters, but with auxiliary variables, you are also able to have a more complex model, like segmentation model or convex or non-convex model with potentials that are not necessarily Gaussian, but that are conditionally Gaussian. Okay. So the main idea is to split the variable. If you are in optimization approach with the maximum a posteriori, what you usually do is to minimize along the set of parameters given the other, and minimize the other parameters given the first one. If you do this in the Bayesian context with a posteriori law, it leads you to the standard Gibbs sampler, when you must simulate a set of parameters given the other, and simulate the other given the first set. Okay, and you iterate. And this is what I say when you have here a conditional Gaussian law given these parameters. So jointly, you don't have necessarily a Gaussian law, but conditionally a posteriori, you have a Gaussian law. And if you are able to simulate efficiently this law, you can do a lot of things. So this is our context here. So we want to simulate this Gaussian law. So we want to do Gibbs sampler, and you want to simulate this conditional Gaussian law, where you have a posterior mean and a posterior precision, or a posterior covariance matrix. And the problem is that your unknown is quite large. So we consider that we have more than 1 billion of parameters. So the mean can be quite difficult to compute, but if you want to simulate a sample from this law, you also need to have, you also must have access to the covariance matrix. And the second problem, which is very large, because if your unknown is more than 1 billion, the covariance matrix is 1 billion per 1 billion. Okay. And the second problem is that since you are in a Gibbs sampler, this covariance matrix and this posterior mean may change at each iteration. So it depends on theta. So if I write some details about this problem that I will reuse after, you have here your linear forward model, you have a conditional prior law, conditional. So your prior law may not be Gaussian, but we consider that are conditional Gaussian for the noise and for the unknown with their mean and their covariance. So you have your prior covariance, your prior mean for the noise and for the unknown. And if you include that in your posterior law and with your likelihood, you obtain a precision that writes like this with your forward model and with your prior covariance for the noise and for the prior. And you must simulate a sample that follows this covariance, and you must inverse it to compute the mean. Which is a classical linear mean square that correspond to the minimum of this criterion, because you know that the mean is equal to the map in the Gaussian case. So this mean can be seen as the minimum of this least square criterion. And the inversion of this matrix can be quite problematic, since it's very large and change at each iteration. So at each iteration, you must simulate, you must compute a new mean, and you must simulate a sample with the correct covariance. So to do this, there is, of course, some existing tools. So there is a Cholesky factorization of the covariance. If you can do this, you just need to simulate a white Gaussian law. You apply your factorization, and X follows the correct covariance. But you need to do the factorization of the inverse of the matrix. You can also do the factorization of the precision and not the covariance. And in that case, you just have to simulate a wide Gaussian nose and resolve this linear system. It's more difficult than this case. You don't have to compute the inverse, but you need to solve the systems. But since this matrix is triangular, the resolution is very easy. But you first need to have the factorization, the inverse of the matrix. If your precision follows some structure, for instance, you can make a diagonalization in the Fourier space. In that case, you just have to simulate white Gaussian noise also, and correlate them by applying a diagonal matrix that contains the eigenvalues of the matrix, and apply the passage matrix. In image, it's often the case with the deconvolution problem, where here you have the fast Fourier transform. So doing this is very easy. If you are not in this case, so here we cannot use these tools because the matrices are too big, so you can't do a Cholesky factorization. We are not in a case where we have a specific structure, so we can't just do diagonalization of the matrix. You can use other algorithm like the per pixel Gibbs sampler. It's okay, you can do this, but it will be very slow because you do per pixel sampling and pixels are very correlated. There is also other algorithm like MALA or HMC that are iterative. And the problem is that they are based on gradients. So it's an advantage, of course, in high dimension, but it's a first order methods. And to have a proof of convergence, you must have a fixed step. And in ill conditional problems, the steps will be very small. So this kind of algorithm are quite slow. So what can we do? So this is our proposition. And this proposition, finally, when we published and we continue to read the literature, we find that our idea were used or mentioned or evocated in other paper. So it is not exactly what we published, but it's quite similar, and we'll see after a while. So this is all this paper we found that mention a similar idea of ours. The idea is to do a well-chosen stochastic expression. So since you want to simulate the posterior law, you must do stochastic simulation, and to rely on optimization algorithms that are known to have a good deal with a very large correlated unknown. So what is our proposition that we call the perturbation optimization? If you simulate from the prior law, so here you have the prior law for the noise and the prior law for the unknown. So it implies that the mean are easy or available. For the noise, it's often the case, it's 0, and for the unknown, it's often 0, 2. And you are able to simulate so central Gaussian law with easy covariance precision. And also it's often the case because the correlation are diagonal, or if they are correlated, they are often stationary. So you can do this by Fourier sampling. So if you are able to simulate under the prior law, you can take the original criterion, so the criterion here that expresses the linear mean square, or the mean of your target law. So you take the original criterion, and instead of using the original prior mean, you use your sampled your sample. So we call this a perturbed criterion. And it's a usual linear mean square with just different mean. And if you look at this expression, we can show that it's follow. So the minimum of this criterion follows the original posterior. So if you are able to simulate under the prior law and you do the resolution, it transforms the prior sample into a posterior sample. So you have two points. You must be able to simulate the prior law, but it's often easy. And you must be able to compute linear mean square, which is also very standard and very common and quite easy. Here it's the proof. It's relatively easy. It's standard linear algebra. So you know it's Gaussian because it's Gaussian samples and you apply a linear transformation. So you know that x hat is Gaussian. So you just need to compute the mean and the covariance. So you compute the mean and you see that it follows the posterior mean. And if you compute the covariance, you see that it's Q minus 1. So this algorithm, finally, is quite powerful because it's compute at the same time the correct mean and the correct covariance. If you don't do the perturbation, the algorithm compute the correct mean, of course. It's a linear mean square. And it's not necessarily easy because you need to inverse the matrix. But if you make the perturbation, you compute the correct mean and the correct covariance. So you have a sample with the correct covariance. So you solve at the same time the two difficulties. Here it's another formulation from Gilles Lavert. That shows that it's another way to express it. If you are able to simulate a sample with Q covariance, then the solution of Qx equal epsilon, so you simulate this one, then X follow the law with the inverse covariance. Okay, so this is what I said just before. If you are able to simulate under the prior law, when you solve the system, you have samples under the posterior. Sorry. The PO formulation just shows that it corresponds to mean change. Okay. So here it's an illustration. You want to simulate this posterior law with this mean and this covariance. And what the PO algorithm do is to produce perturbed criterion. So you have the same criterion that is shifted, okay, perturbed. There are also quadratic criterion, and what we see is that the covariance does not change. Okay, and the minimum of this perturbed criterion follow the original law. So you generate a lot of this perturbed criterion, you estimate or you compute the linear mean square or the solution of this criterion. This is what I do here. And if you make an histogram, you can see that it corresponds to the original target law. Okay, so there is of course some limitation. The first one is the effect of truncation. Since you want to do optimization and you are in a large dimension, usually you don't do all of the iteration. For instance, if your one is 1 billion parameters, you must do 1 billion iteration with the conjugate gradient algorithm. So of course you don't do all the iteration. And here, if I do, so it's in 2D, if I do only one iteration, this is what I obtain. So there is no bias on the mean, but you don't have a correct covariance. Okay, you can see that in the long axis, you have not so good exploration. And of course, it corresponds to the smallest angular value. So some comments about this algorithm. It's quite simple because you need to do simulation of the prior Gaussian fields, which are often easy, and you must do a quadratic optimization, for instance, with preconditioned conjugate gradients, which is very standard and available in all the toolbox like SciPy, Julia, or PyTorch. It's able to simulate a lot of non-Gaussian law with latent variables, with a conditional Gaussian law approach. You can have a correlated Gaussian field, non-stationary Gaussian field. You can do segmentation, or you can do Gaussian mixture, for instance. And with Gaussian mixture, you can do segmentation, but also a non-convex potential. And since we can include this algorithm in a full MCMC approach, you can do estimation of the hyperparameters with a case sampler. You can do myopic or blind inversion. And of course, and this is the original motivation, you can estimate the second order of the posterior law. So you are able to estimate or make a quantity uncertainty quantification. So some illustration of this algorithm. We use it in different cases. So the first one I show you in the super resolution. We work here in the simplest case, of course, to just show the potential of the algorithm. You have the movement of the sampling matrix, the correlation or the blurring operator. We consider Gaussian prior for the unknown and for the noise, and we consider that the hyperparameters follow gamma law to have a full unsupervised estimation. So we have this full posterior law. If we marginalize on the hyperparameters, we have a student prior law on X, and we can do Gibbs sampler to estimate the unknown and the hyperparameter. And we obtain this kind of results. So this is a true image, data, and the reconstruction. So what is important here is that it's fully unsupervised, and there is fully unsupervised. Okay, the algorithm never see any data, and it's able to of course reconstruct the image, but also to estimate the hyperparameters. This is what we see here. It's a Gibbs iteration. We see that the hyperparameters for the noise and the hyperparameters for the image quickly converge in maybe 20 iteration. So we need to do 20 conjugate gradient to have a point here. Okay, and since you have a point here, we can do after a map estimation to just stop the algorithm. If you are interested by the uncertainty, of course, you need to produce more samples to estimate the second order moment. Here you have the histogram of the chain. So we can see that this image, there is no human that tune any hyperparameters to have this image, and you can show that it's very, very similar to an image produced with the best hyperparameters that you can tune, and you know the true image. Here it's an example on real data. It was quite old now. We do other things now, but it's a super resolution problem from data that are from the Spire camera of Herschel. So Herschel is a space telescope, and the Spire camera is not a usual detector. Because it's worked in infrared. Okay, so it's more complex than classical super resolution, but we can show that it's quite similar. And again, the forward model is not stationary, so you can do Fourier analysis to produce samples. Here it's a classical approach, and here it's our proposed approach. So we can see that we are able to handle the missing data. We do deconvolution effect or unblurring effect, and this algorithm never seen one data. It's fully unsupervised, the hyperparameters are automatically estimated. Here it's a slice, so will not show here. Here I showed, so it's for the previous example on Spire, and what I want to show is first the correlation between the hyperparameters. We can see that hyperparameters are of course correlated between them because it's tunes the compromise between the prior and the likelihood. And more interesting, the uncertainty quantification. So here I estimate the second order moment, or I estimate the uncertainty or the confidence we have on the image. So we can see that when we have more redundancy, when you see more often the pixels, you have less uncertainty. Here is another example on biological image microscopy in SIM, structured illumination microscopy. So you have again a forward model that is not stationary. The idea is to reconstruct. So you have a PSF that remove all the high frequency. So you have a true cutoff. And what you want to do is to reconstruct this high frequency by amplitude modulation that introduce this high frequency here by aliasing. Okay. So the model is not stationary, so you can do just deconvolution. So we propose an inverse problem algorithm that uses this PO algorithm to estimate the hyperparameters, and you are able to reconstruct this kind of image with high frequencies that were totally unseen, unavailable in the data. And again, this algorithm never see one data. It's fully unsupervised. And here it's again the uncertainty quantification on the previous image. So when you have more photon, so when you have less noise in the data, you have less uncertainty. Okay, so here it's an image of the forward model, how the data are measured, and here it's an estimation of the uncertainty. So I was very pleased to see this image because we can clearly see the advantage of the MCMC and Bayesian approach. So what about the main limitation, which is the truncation? So there is ongoing work. The first approach was proposed by Gilles Lavers that introduced metropolis testing, the steps in the resolution of the linear systems, and they call it RGMCMC or RGPO because they use the RGMCMC theory. There is another approach proposed by Colin Fox, which use the fact that the conjugate gradient do conjugate factorization of the matrix, like for Fourier, and so he produced a conjugate direction sampler. The problem is that it can be trapped and suffer also from the truncation. So with Olivier and Jean-François, we propose other algorithm that we call it gradient scan Gibbs sampler that use this CDS approach, but we still use perturbation to have a better convergence. Okay, so it's work, and now we most work on non-Gaussian modeling. So, but the non-Gaussian modeling, the PO is able to simulate conditional Gaussian law. So it's Gaussian when we know the hyperparameters, but we can use this hyperparameter to do other things like segmentation or Gaussian mixture. So personally, I mostly work on Gaussian mixture, and I work on two kinds of Gaussian mixtures: the location mixture of Gaussian, where you do not change. The advantage is that you do not change the partition function, so you can still do fast simulation with Fourier, for instance, or the scale mixture of Gaussian, the continuous scale mixture of Gaussian, when you do a mixture on the variance, and with that you can do Laplace modeling or student modeling. The problem is that you change the partition function, and if even you have a stationary forward model, you are sure that you don't have a stationary posterior field. So if you do location on the mean, so you make a continuous mixture of a Gaussian law on the mean with a prior law on the mean. So you do this, of course, on the prior field. So you have a regularization operator here. If you choose Laplace prior for the latent variable, you can show that you have a convex potential that we call log F. So here is a log F potential, and it looks like a burr, and we show that it's convex because you have here the convolution of two convex functions, so it's convex. So here it's the first result we obtain. So we are better now. It's in deconvolution. Here you have the quadratic reconstruction. So you can see that you have a classical limitation of the quadratic restoration with ringing here, and here you have what we obtain. So you can see that it's really more clean. You do edge preserving estimation, and again, here it's fully unsupervised. The algorithm never see one data. We estimate the hyperparameters. And here, since we are doing MCMC, we are able to estimate the second order moment. So this is what we do here. We have an estimation of the uncertainty, and we can see that we have more uncertainty on the edge. Which is natural since we are doing unblurring. To reconstruct the edge, you need to have a high frequency, and the high frequency are those who are filtered by the blurring effect. So of course, you have more uncertainty. Actually, I work on a scale mixture of Gaussian that are a little bit more powerful. And this is our first result. So again, we have the standard deviation where we see that we have more uncertainty on the edge. And we have also the estimation of the auxiliary variables. We can see that we detect the edge also since we are doing a convex restoration. So as a summary, I present a strong tool, so a very powerful tool if you have a Gaussian field that are non-stationary and large. And when I say large, it means that you can do Cholesky factorization, and all the variables are correlated between them, and you want to preserve this correlation, of course. If you want to do approximation with diagonal covariance, of course you can do this. What we wanted is to preserve all the correlation. I show that we are also able to do non-Gaussian restoration with this PEO algorithm by using hidden variables. And I show some result on super resolution, myopic inversion in astronomy and microscopy. There is some limitation and perspective, so the effect of truncation is almost resolved. I don't remember what I want to say. Yes, if you use direct simulation of the correct law, you don't have the effect of truncation. This is what we work with GSGS. We can do unsupervised convex inversion, so this is our work in progress. And even if we are able to produce samples quite quickly, it's finally quite slow since you must do a lot of system resolution. So we work on acceleration, notably with Jérôme Midier. So it's also work in progress, the acceleration aspect. I finished. Thank you for your attention. And if you have any question, don't hesitate.
Thank you very much. Merci beaucoup. So very interesting subject with many important contents. And I am sure that there are also many questions. Let's start by the audience, if there are questions. Who wants to start?
Oh, I have a question.
Mm-hmm.
So, François, you mentioned in the first part of the work, you present the sample algorithm, and in that algorithm, there is a truncation effect in the result. So it means that for some dimensions, the law is not how to say, the law is not well determined.
You speak about
yes, this one.
Okay.
So I just wonder, do you have an example of this truncation effect on the image result? So yeah. I just want to see what will the result looks like with this truncation effect.
Okay, so I said there is three regimes of effect. The first one is when you really don't do enough iteration. In that case, the chain of the hyperparameters does not converge to the true stationary law. And what you usually see is over-regularization. So you have here too smooth image, okay? But it's really when you don't do enough iteration. So for instance, you must do, I don't know, 50 iteration and you only do 20, okay? So you clearly see that there is over blurring or over regularization in the image. The second regime is when you do enough iteration, but there is a small bias. And in that case, what we see is that you have a correct convergence of the hyperparameters. You obtain an image like that, but it's mostly on the covariance that you have an effect, because you have the correct mean, so the mean corresponds to this image, but you start to don't have a correct estimation of the covariance, and so it's what you see is on the estimation of this kind of results. So there's the second order estimation or the uncertainty quantification. In that case, you don't catch the small details like the pattern here, that you don't see it. So you have a biased estimation of the covariance. And on the image, you don't have a strong effect, but maybe on very small details, you don't have a perfect reconstruction of very small details. Okay. And if you do a lot of iteration, so you are sure that you have the correct convergence, if you use a RGPO, for instance. And in that case, we see that there is very small variation in the image, in the details, and very small variation in the standard deviation. Okay, so what I usually say is that you can truncate the iteration. You can truncate because if you want to have a very good reconstruction of the very small details, finally, it's still in the uncertainty. Okay, you estimate these very small details, but maybe they are erroneous with respect to the true image. So it's fall under the uncertainty, and it's not very problematic. Okay, so what I usually say is that you are not enforced to do a lot of iteration to avoid this truncation effect. You can reduce the iteration to have a faster algorithm.
Okay, I see.
François, another point about the truncation is how many samples we are generating, we need to generate to be able to compute good values for the mean and for the variance.
Yeah. So again, so for the mean, I think that you see that you have here a burning period. What I see usually is between 20 and 50 iteration to reach the stationary state. Okay. Since you are at the stationary state, you just have, if you just want to have the mean, you can stop, take the value, okay, and compute a map.
Mm-hmm.
So 20, so you just want to estimate the hyperparameter, so you have the hyperparameter and you compute the map. If you want also the uncertainty on the image, so you need to still have some samples in the stationary state.
Yes.
And in that case, if you just want the second order, 20, 50 samples also, and you have a good estimation of the uncertainty.
Okay. Lee, you can continue.
Yes, and I was also want to ask the same question. And then you mentioned that you're working on to solve this problem, the truncation problem, and so maybe it's a work in progress, or you didn't take a lot of time to present the details. But for example,
the effect of truncation, I think it's almost resolved because we have the RGPO algorithm that is quite good to be sure to have, because the RGPO algorithm do two things. The first one is that it ensures that you have enough iteration, and at the end, it do a metropolising steps. So with the metropolising steps, you are sure that you have the correct sample, the correct law. So I think the effect of truncation is almost it's resolved. So if you don't want to have the truncation effect, you can use the RGPO algorithm. Where we have more work in progress on the acceleration and the convex restoration.
Okay, the RG. Do you have the reference paper about that?
Oh yeah, if you. If you look for, maybe I would just launch. Okay, Scholar, Gilavert, Idier. It was a signal processing. Yeah. Efficient Gaussian sampling for solving large-scale inverse problem using MCMC. So it's a paper from Gilavert, Saïd Moussaoui, and Jérôme Idier. You can do a screenshot if you want.
Okay, thank you.
And maybe I can show if you want a live illustration of this kind of algorithm. So it's a Python program. We are trying to do unsupervised convex deconvolution. And so again, it's unsupervised, so there's no need for learning. So here we have the measure, so it's a blurred measure with the zoom here, and here we have the quadratic estimation, which is also unsupervised. So it's very fast because it's only deconvolution, and we can see that we have some ringing effect. So the quadratic is known to have some limitation. Okay, so if I close, okay, so now here you see the live algorithm that do MCMC. So we try to do the deconvolution, and it tried to estimate the hyperparameter with a convex potential. So we do edge preserving. So it's faster than that because we can see that the drawing time take 75% of the iteration. Okay. So here you have samples. Here you have the current mean, and here you have a standard deviation of all these samples. And you see it's already finished with 2,000 samples. And here you have the auxiliary variables. So we are doing location mixture of Gaussian, and these variables catch the posterior mean of the posterior mean of the prior model. Okay. And here we can have a zoom. So here it's a quadratic reconstruction with a zoom, and here we have the convex restoration with the zoom. So we can see that it's really much better. And again, it's fully unsupervised. So I think it's quite powerful approach. It's work. Whatever you put as a data, it will work if the forward model is respected.
But this is very, very interesting, and we may try to use infrared images that we have to see what we can get. Where was the address?
What about what?
The link. The link.
The link for this paper. For this work, it's relatively old now, because now I work more on scale mixture of Gaussian. Okay. No, I work more on acceleration and scale mixture of Gaussian because if you don't do so, it's work in progress. I don't have a paper to show you. So here it's just a case in just deconvolution. This is why it's very fast, of course. But you can see that the prior model is quite powerful. So we want to use this prior model now in a more complex forward model. But it's finally, since you must do PO algorithm, we work on the acceleration with Jérôme. But for this convex restoration, yeah, you can refer to this paper, for instance.
Lee, do you want to continue?
That's all. Thank you very much.
Okay. Thank you very much.
Yeah. Other questions in the audience? Do not hesitate, if any. Okay, so no questions, no other remarks. François, there are a lot of interesting content in your presentation, and I think that we need in the future to have more seminars in more detail. And I think that a kind of comparison of these different methods that you mentioned, it will be very interesting.
Yeah. Also with these algorithms like HMC, NUT, or MALA,
yes,
that are quite standard now and available in most of the toolbox.
Yes, and in particular, just know we are working on infrared images, and at one time we need to do a kind of blind deconvolution of these infrared images, because infrared images have very low resolution, and very often when we want to do a good segmentation of these images, we need to increase the resolution in some way, or at least obtain a good segmentation. I think that when you showed the auxiliary variables which represent in somehow at one time it represents the contours and other variables which represent a kind of segmentation of the image. That will be very interesting to see and to see what these methods give on these infrared images.
Yeah.
And I think that this as I mentioned, one of the objectives of this seminar is to see what we can do in the future together in a kind of cooperation. For example, exactly this infrared image segmentation, super resolution and segmentation is one of the subjects on which we are interested. Another one is a kind of data fusion or image fusion between visible and infrared images. Yes.
Yeah.
Okay, so I think that we will surely propose, or we will try to see what are the subjects on which we can continue to work on.
Sure, with pleasure. Okay.
Okay.
Thank you very much.
Any other comments or suggestions, questions? If not, I propose you that if you can, everybody shows. Ning, I see that you. Yeah. Do you? Your microphone is not open.
Yes, it's okay for me.
Okay.
The similar question that you have asked.
Okay.
Okay. So if no more questions, I propose that everybody shows himself, if it is possible, and we say thank you to François and Stefan. Your microphone is not open. If you have a question.
No, I don't have questions.
Okay.
Thank you. Thank you.
Okay. Okay, so thank you very much again, François, and see you soon.
Yeah.
I hope.
Okay. Thank you. Bye to everyone. Thank you. Thank you again. Bye.